So, hi guys, this is Dr. Edwards again. I want to talk to you about the statistics that's important in quantum mechanics and how processes that we already knew in mathematics gets converted over to quantum mechanics. So let's start here. Okay, so this is the beginning. What is the probability in the various cases here? And this is by age, just to get started. One person is 14 years old. One person is 15 years old. Three people are 16 years old. Two are 22 years old. Two are 24. And five are 25. We want to calculate what is the average age. And the value is going to be 21, which is a number that's not even in one of the ages listed here. So this is the way the random statistics come into play. So the number of person that's 14 years old is 1. The number that's 15 years old is 1. Number 16 years old, 3. Number that's 22, 2. 24, 2. 25, 5. Okay, so we're going to now come up with the idea. The total number of persons in the room, you normalize the probability with having capital N equal to the number of persons in the room. So you sum over J going from 0 to infinity, and at J equals 1, J equals 0, 1, etc., counting the number of entries you have. And you go on here and you find that the probability for each entry is n of J divided by capital N. All right, so look at this now. And so these become what we call a histogram. One person at age 14, one at age 15, so n sub J is plotted on the vertical. 3 persons here at age 16, none in this middle range. 2 at 22, 2 at 24, 5 here at 25. Okay, so we go on here and we see that the probability of any one is P sub J. Then if you add up all of the probabilities, P sub J's, it should be normalized to 1. So that's where that normalization comes from in quantum mechanics, that the probability of getting the various values that you get, they all should add up to 1. So the main value that we want to calculate is not the most probable value. No, the most probable value here will be 25. It is not the median value either, which is 23. What we want to calculate is what's called the mean. And in quantum, we will call this the expectation value. So it's 14 times 1 plus 1 times 15 plus 3 times 16 plus 2 times 22 plus 2 times 24 plus 5 times 25 divided by the total number of 14, and you get a value of the expectation value, average value, being 21. So that's where we get the notion of this. And so now this becomes the notation that we use in quantum mechanics. This less than symbol J and greater than becomes what we call the expectation value of a quantity. And so not only can you count the index in this manner, J is an index, but any quantity then that you have, you can find the expectation value of J squared. Same methodology. If J squared occurs with a probability of P sub J, then this becomes the expression of calculating the expectation value of J squared. Then for any function, if you will, function of j, the expectation value of f of j is some j going from 0 to infinity of f of j times p sub j. This is probably 1.9 is the most important expression here pertaining to quantum mechanics. All right, so this is the histogram. Okay, then we want to, so we go here now and find what is going to be called the variant and the standard deviation from the means. It is called sigma here. Sigma is the square root of the expectation value of j squared minus the square of j. That's called the standard deviation from the mean. And we always want to calculate that in quantum mechanics. Whether we actually do it or not, it is always available for you to make these calculations. All right. So this is what I've done so far is true for discrete statistics. In continuing variable statistics, you have a similar kind of behavior occurring. And you go on here and it turns out that the probability that an individual chosen at random lies between x and x plus dx is given by the probability density times dx. And so now we can talk about the probability between a and b as the integral from a to b of the probability density. Now, so this is where we get into normalizing then. If you integrate then from negative infinity to positive infinity of the probability density, it must be equal to 1 in quantum mechanics. If there's just one particle, it ensures that that one particle is in that range. And now similar what we did for the discrete case, now this is for the continuous case. The expectation value of the position coordinate x is the integral from minus infinity to positive infinity of x, the probability times dx. And it's similar then for f of x, go on, and we can finally calculate then the variant or the standard deviation from the mean. This is a good example problem here in classical physics. It's suppose I drop a rock off a cliff of depth h. I don't like the word height. Depth is better because, in my opinion, the origin is at the top of the cliff. So you're looking down into a depth h. Now, so as it falls, I snap 1,000,000 photographs at random intervals. On each picture, I measure the distance the rock has fallen. What is the average of these distances? That is to say, what is the time average of the distance traveled? It turns out that the answer is here, h over 3. H here is not h bar. It's not the quantum h. This is just height. So since the body is falling, most of the time, the rock is above h over 2. So you might want to think that the average value will be halfway, but it's not. It's only a third. And you go through the math here. So I'm going to leave this here so that you can see it long enough. Okay, so you can stop the play. Go through this problem here and understand how we get that the probability density is 1 over 2 square root of h over h times x. And then you integrate that expression here to normalize the expression to make sure it's equal to 1. And then you can find the expectation value of the height. Now let me talk to you quickly then about quantum mechanics, a problem that we have to do. And so let me see if I can get this to open up a little bit more. I may not be able to. Okay, so I think I'll stop here and I'll put this part on a separate video, okay? Have a good